Okay, so first example, we're given this function and we want to find where it's increasing, decreasing, and any local max or local or absolute max or mins if they occur. So because it's a function, it's not giving us the graph. First thing that we want to do is we want to find our critical points. And so remember, critical points, we want to look at the derivative of our function and find where it's equal to 0 and undefined. And so first thing you want to do is take your derivative. So taking the derivative of f with respect to theta, derivative of 6 theta is just 6 minus the derivative of theta cubed. So bring down our power, subtract 1 from the power, we get minus 3 theta squared. So we now want to find where this equals to 0 and where this is undefined. Well, this is defined everywhere. If you look at the derivative, it's a polynomial. So there's no places where it's not defined. So we're okay with this. We don't have to worry about it. But now let's look at when it's equal to 0. So we're looking at when is 6 minus 3 theta squared equals 0. So determine how you want to solve the equation. This one, we could isolate our square if we wanted to, and then use the square root method. So if I added 3 theta on both sides, I would get 3 theta squared on both sides. I would get 3 theta squared is equal to 6. I can divide both sides by 3. I get theta squared equals 2. So take the square root of both sides. Well, there's 2 values that you can square to get positive 2. So plus or minus root 2. Okay, so these are our critical numbers. Once I've done my critical numbers, I like to put those on my number line. So smallest to largest. And so my smallest critical number is negative root 2. And my largest critical number is positive root 2. So we want to see where this is increasing and decreasing. We know if we plug in a value and we get the derivative, plug it into the derivative and it's positive, it's increasing here. So we want to test a number on the left of negative root 2. We want to test something in between negative root 2 and positive 2 and something bigger than root 2. Never plug in the critical number. We're just testing each interval on a side of a critical number. So in this case, we have 3 intervals we have to test. So choose any number to the left of negative root 2. So how about x equals negative 2? So that's smaller than negative root 2. And we want to plug that back into the derivative function. Really, we're only worried is this positive or negative number. So if it gets really ugly, we can always just plug it in and think, is this going to come back positive or negative? So plugging in negative 2 wherever I see a theta in my derivative, I get 6 minus 3 times negative 2 quantity squared. So I know if I square negative 2, it's 4 times this 3 in front. So that's going to be a minus 12. So 6 minus 12, this number is smaller than 0. So I know that my function is going to be decreasing to the left of negative root 2. So now we want to choose some number that falls in between this negative root 2 and positive root 2. So let's choose, how about x equals, if 0 is in that interval, that's usually the easiest. And I shouldn't be putting x really, because these are theta. We're so used to writing x all the time. So theta is 0, this should have been theta equals negative 2. Okay. So again, we want to plug it into our derivative. And if it comes out positive, we know it's increasing. If it comes out negative, it's decreasing. So f prime of 0. So this would be 6 minus 3 times 0 squared. So this number here is bigger than 0, it's 6. It's increasing in between -2 and √2. So now choose something on the right of √2. So any number to the right of √2. So how about x equals, or not x, theta equals 2. So if we plug this back into the derivative function, we want to see, is that positive or negative? 6 minus 3 times 2 squared. I notice that this is smaller than 0. So this is going to be decreasing. So we now have our intervals where it's increasing and decreasing. So it's decreasing. Notice that it's decreasing from -∞ to -√2. And then union, it's decreasing from positive √2 to infinity. And it's increasing on this interval between -√2 and positive √2. And so now look and see what's happening at that critical number. If we're changing direction from increasing to decreasing or decreasing to increasing, we can see that we have max or mins. And so at -√2, since we're coming down and then changing direction and coming up, we know that we have a min when x equals, not x, okay, theta equals -√2. I don't know if that's an absolute max or an absolute min, but we can talk about this in a minute. And if I'm increasing between -√2 and positive √2 and then decreasing, notice that this right here is a max. So I have a max when theta is equal to √2. Okay, so to find those max and min values, I need to plug that into my original function. And my original function is this f of theta. So f of -√2. This is 6 times -√2, so that's going to be -6√2. Minus a -√2 cubed. So that's going to be a negative and a negative. So plus √2 cubed. So it depends on, do they want you to keep this in exact form or do they want you to plug this into the calculator? So let's just plug it in to the calculator and get an estimate of what that y value is there. So we have -6 times the square root of 2 plus the square root of 2 cubed, or the square root of 8. So actually, we could clean this up a little bit and get a better exact value, but let me do this too. So this is -6√2. This is plus the same thing as the square root of 8. So this is -6√2. 8 is 4 times 2. Square root of 4 is, so this is 2√2. So a -6√2 plus a positive 2√2. This is a -4√2. Which should be about -4.4. Oops, which I didn't get the same thing, but I should have. Let me just check my work real quick. This is approximately -5.7. Okay, so that's the min value. And we know where it's occurring at. And we would do the same thing now, and we would plug in positive root 2 into our original function. And so if we plug in positive root 2 into our original function, this gives us 6 root 2 minus root 2 quantity cubed. So that is 2 root 2. So this would give us back 4 root 2, which is equal to negative 5.7. No, it's positive 5.7, sorry.
Professor, the first time you did it, you plugged in a negative root 2, and then
Oops,
it kind of dropped.
hold on. Okay, so right here, this should have been a plus. But when I plugged it in, I plugged it in as positive root 2. And our high value is, so the max value is 5.7 when x is positive root 2. If you use things, facts about functions being even or odd, we could use that fact to understand what's going on with a graph and not have to plug in as many numbers. But I normally don't tend to think about that when I'm doing this. The other thing, these are just local. And the reason I know this is because of how our graph is looking. I know it's decreasing until I hit negative root 2, and then I'm coming back up and I'm increasing until I hit x equals positive root 2, and then I'm decreasing forever. And so if that's the case, there's no highest value and there's no lowest value. And so these would be local max and local mins. So knowing the end behavior of your graph, if your function is always continuous, is helpful to see if there's an absolute max or an absolute min. Okay, so this next example, we're doing the same thing, finding intervals where it's increasing, intervals where it's decreasing, and any absolute or local extrema if they occur. And so we're given f of x is equal to x squared all times the square root, and underneath that radical is the quantity 5 minus x. I notice here, because we have a radical, that our domain is limited. We are not going from negative infinity to infinity. So sometimes thinking about the domain is helpful. And so because this is a square root, the index is even, we can't have a negative underneath the radical and get back a real number. And so 5 minus x, I know has to be greater than, this is not in the denominator, so it can equal 0. So 5 minus x has to be greater than or equal to 0 in order for us to get back a real number. And so I'm just solving for my domain. If I add x to both sides, I get 5 is greater than or equal to x. To me, I like to look at this when the x is on the left, so I can rewrite this as x has to be less than or equal to 5. So I know I have an endpoint of my domain. So my domain, so everything is coming from negative infinity because it's less than or equal to 5, to 5 with a closed bracket. Okay, so now let's look at finding our critical numbers. And so finding the critical numbers, we need to look at finding the derivative, finding where it is equal to 0 and where it's undefined. So let's take the derivative, but notice that when we take the derivative, actually before we take the derivative, let's rewrite this a little bit. So we have f of x is equal to x squared. We're going to treat that as our first term. And then let's rewrite the square root as 5 minus x raised to the 1/2 power. So now when we take the derivative, we're going to have to use that product rule. So derivative of the first, so derivative of x squared is 2x times the second. I'm going to leave that in square root form in this case, 5 minus x plus the first, which is x squared, times the derivative of the second. Okay, so the derivative of the second, we're going to have to use the chain rule. So derivative of the outer, we'd have 1/2 of the inner, 5 minus x, subtract 1 from 1/2. So 1/2 minus 2/2, so negative 1/2. Don't forget to take the derivative of the inner. So the derivative of this inner piece, 5 minus x, is negative 1. So let's clean it up a little bit. So this is equal to 2x square root of 5 minus x. I'm going to pull out the minus in front, minus, we're left with an x squared in the numerator, all over 2. Let's bring this negative exponent down, that whole piece, and rewrite it as a radical. So square root of 5 minus x. Okay, so we need to find where this is undefined, and we need to find where it's undefined, but defined in our original domain, and where this is equal to 0. So let's start with equal to 0. So if we do that, we get 2x square root of 5 minus x squared all over 2 square root of 5 minus x. We're looking at when is this equal to 0? I would probably clear my fraction. And I notice I can clear my fraction by multiplying both sides of my equation by my denominator. I only have one denominator. So 2 square root of 5 minus x. Whatever I do to one side of the equation, I gotta do to the next or other side. And so if I distribute this 2 square roots of 5 minus x to the first piece, well, I have that 2 times 2, so that's 4. I have this single x, but square root of 5 minus x times square root of 5 minus x, that's just, and I need parentheses around the whole thing, 5 minus x. When I distribute it to the second piece, the denominator goes away and I'm just left with my minus x squared equals 0. So let's distribute that 4x. So 4x times 5, I get 20x minus 4x squared minus x squared equals 0. So notice that this is a quadratic. Let's combine like terms. I have a negative 5x squared plus a 20x equals 0. So notice that we can factor out greatest common factor. Let's factor out a negative 5x, and that would leave you with a positive x minus 4 equals 0. So we're looking at when is negative 5x equals 0 and when is x minus 4 equal to 0. So when x is 0 and when x is 4. I would look to see, is this in my domain? My domain was negative infinity to 5, including 5. So these are my domain. Those are our critical numbers. Now we want to look at when is this undefined? Well, it's undefined when we have a negative underneath the radical, but it's also undefined when we get 0 in the denominator. So f prime of x is undefined at when 5 minus x equals 0. Or x equals 5. So it's undefined at x equals 5, the derivative, but it is defined in our original function. Okay, so on our number line, we're coming in from negative infinity. We know that we have to hit 5. So we're not even testing anything to the right of 5. And our critical numbers going from smallest to largest, 0 and 4. So notice I have 3 separate intervals I have to test. So something that is less than 0. So choose a number less than 0, and we want to plug that into the original, not the original, the derivative. So how about x equals -1? So if we look at f prime of -1, that would give us 2 all times -1 square root of 5 minus a -1, so 5 plus 1 minus -1 squared all over 2 square root of 5 minus -1, so 5 plus 1. If I think about this as positive or negative numbers, notice that that first term is a negative. It's 2 times -1. Notice that second term, and when I square the -1, that's positive, but I still have this negative here. So if I plug this in, I don't care what the number is, I just care the sign. I notice that I'll get this number is smaller than 0. So if that's smaller than 0, that tells me that my function is decreasing on the left of x equals 0. So now you want to choose something between 0 and 4. So choose any number between 0 and 4. So how about x equals 1? Again, we want to plug this into the derivative. So we're going to look at f prime of 1. Should be the derivative. So this would equal, 2 all times the square 1 square root of 5 minus 1 minus 1 squared all over 2 square roots of 5 minus 1. So I need to know, is that going to be a positive number or a negative number? Well, square root of 4 is 2. I can see that that first term is going to be 4. And I see that that second term, I'm going to be subtracting, I think it's 1/4. So that's going to be a positive number there. So this would be greater than 0. So this is increasing. And then let's choose something to the left of 4, but smaller than 5. So how about x equals 4.5? So plugging that into the derivative, and we want to see, are we going to get a positive number or a negative number? So we got 2 all times 4.5 square root of 5 minus 4.5 minus 4.5 squared all over 2 square root of 5 minus 4.5. I'm not quite sure if I'm positive or negative, so I would go through and start doing more. I should put in green, but I didn't. So this would equal 9 square root of 0.5 minus 4.5 squared, which is 20.25. All divided by 2 square root of 0.5. So if I divide that by 2 square roots, need parentheses around the whole denominator, 2 square root. This piece here is about 14.3. And 9 times the square root of 0.5 is 6.3. So I see that this is going to be less than 0. This is less than 0, it's decreasing. Okay, so I can see what we're getting. If we're going from something that is decreasing at first, then it's going to turn around and it's going to increase. And then it's going to turn around and it's going to decrease. So same sort of reasoning as before. I don't have any absolute max or absolute mins because of the end behavior of the graph. So I can see that I have a local min when x equals 0, and then increasing to decreasing, I'm going to have a local max when x equals, oops, actually I lied. This has to stop at 5. And I'm not sure where that 5 is. So it's possible that this does have a local min. It does have a local min. So local max, we said at x equals 4. And local min when x equals 5. So to figure out those values, we have to plug it back into the original function, which is way up here. So bring it down and plug it in. Oops. Darn it. I didn't push save. Okay, so Control C. Okay, so we want to plug it back into the original. So if we plug in 0, f of 0, I can see I automatically get 0 back. 0 times anything is 0. So we have a min, x equals 0, min is 0. If we plug in 5, well, square root of 5 minus 5, well, that's the square root of 0 times 5 squared, that's going to be 0. So f of 5, I also see is 0. So if they're the same y value, we can treat that they're both local min, but they're also both are absolute min. And then the local max, we plug in 4. And so f of 4, 4 squared is 16, all over the square root, or all times the square root of 5 minus 4, which is square root of 1 is 1. So my max value is 16. They also want to know where it's increasing and decreasing. We have that basically on our number line. So we're decreasing from negative infinity until we hit 0, parentheses, union 4, comma 5. Because it's an endpoint and it's included, I would put in the 5 with a bracket. And it's increasing in between 0 and 4. So that's a lot of work right there.